Okay, hey, how's everybody doing? Hopefully you're working on Chapter 8, and we're going to go over Chapter 9 tonight. This will be the last chapter that you'll do for this semester because we're just out of time. Chapter 10, there's some good stuff in it, but it's not going to hurt if we miss it, okay? So this will be our last chapter, and your final will consist of Chapter 8 and 9. I will post that probably early next week, and you'll have till the 8th. I thought it was going to be the 9th, but it's going to be the Tuesday the 8th to finish it because grades have to be in 10 a.m. on the 10th, and so I won't have time to get everything graded and averaged with all my classes, okay? But we'll just take what you have and give you your final grade. Make sure that if you hadn't turned in all of your work that you get that turned in to me also. Okay? By the 8th. That'll be the last day that I accept any work or test. So we're going to talk about rotational motion. So far this semester, or the last couple of chapters, we've talked about just straight line motion, going in a straight line. This is going to be rotational motion. So with rotational motion, we're going to be talking about something in a curved path. So like a satellite orbiting the Earth, or a rotational motion of Earth spinning on its axis, or even like a spin top like you had when you were a kid and you would spin it. Those are rotational motion. So it's when the body itself is spinning. Okay? There are three basic systems of dividing angle measurement. The first one we're going to talk about is revolution. Here we go again. Revolution. Okay? With revolution, it's one complete rotation of a body. The unit measurement of rotational motion is the number of rotations. So how many times the object goes around. The unit of rotation, which is used in industry, is one revolution. So the unit, a lot of times you'll hear it said one rev or one revolution. A second system is angular measurement, divides the circle of rotation into degrees. So degrees is another one. So it would be like 360 degrees equals one revolution. Okay? And the last one is radians, or rad. You may hear me say. Radians, and that is approximately 57.3 degrees, or this is more what you might see is 360 divided by 2 pi degrees. Okay, and that's the third type. All right, so a radian is defined as that angle with its vertex at the center of a circle whose sides cut off an arc on the circle equal to its radius, where S equals R, and theta equals 1 rad. So by definition, the radian measure of an angle is the ratio of the length of an arc. So if we had a circle here, and I know it's not going to be perfect, but look in your book on page 232, and you have this little slice here. This would be theta, your angle. Let's make that better so you can. Theta. And this is going to be your S right here. This big thick area here. And this will be your R. Okay? So theta is your angle determined by S and R. S is your length of the arc of the circle, and R is your radius of the circle. Okay? So another way to look at all this is 1 rev equals 360 degrees equals 2 pi rads. Okay? And again, just like the other test, I'll give you any formulas and things that you need, okay? All right. Now another thing you might hear us talk about is angular displacement. It's the angle through which any point on a rotating body moves. Note that on any rotating body, all points on that body move through some angle in any given time. So an angular displacement is that. Now, there's also something called angular velocity. And angular velocity is the rotational system, is the rate of angular displacement. So you'll see a formula. It's kind of like a fat W equals theta over t, where omega is the angular velocity, theta is your angle, and t is in time. Okay, so let's look at a problem. A motorcycle wheel turns 360 times while being ridden for 6.4 minutes, 40 minutes. What is the angular speed in revs per minute? Okay, so let's write down what we need. Our time, or what we have, is 6.40 minutes. Number of revolutions, number of revs, is 3,600 revs. And it wants to know what is the angular speed, so omega. Okay, so remember the formula, omega equals theta over t. We have theta and t. No, we don't either, do we? We have that's the basic equations. Oh, okay. So one thing that I didn't show you over here, I'm sorry, is that theta can also be angle in radians, or it can be angle in revolutions, okay? So on this formula, see, we have it in revolutions. So that's going to be 3,600 revolutions divided by t, which is time, 6.40 minutes, and that's going to give us 563 revs per minute, or you also will hear that as 563 RPMs, which that's what we're used to hearing, right? Like on our car or whatever. 563 RPMs. Okay. Now, let's look at another one. So what if we had also, you may have to combine some formulas, okay? So here are all the formulas for linear speed. Theta equals S over R. That was from before. Second one is velocity equals S over R. Remember displacement? And 3 is omega equals theta over t. Okay, so you got to pay attention to what you need to do to combine, okay? So you can work this out and end up with this formula. Velocity equals omega over r. And if you want to see that worked out, look on page 234. It's a really good example. Alright, so remember that, where velocity is v, w is angular speed, and r is the radius. So let's look at a problem. Move this over here. Alright. Now, a wheel of 1 meter radius turns at 1,000 RPMs. A, express the angular speed in rads per second. B, find the angular displacement in 2 seconds. And C, find the linear speed of a point on the rim of the wheel. Okay, so, and it shows you the wheel on page 234. So let's write all of our data. So it says omega equals, the radius turns at 1,000 RPMs. We need to change that to rads per second because it says express the angular speed in rads per second. So we got to convert that. So let's do that first. So omega equals 1,000 revs per minute times that conversion we looked at earlier, 2 pi rads over 1 revolution, times, we also got to change it to seconds, and it's in minutes right now, so minutes per 60 seconds equals 105 rads per second. So now we have this for our first part, which says express the angular speed in rads per second. So now we can work on that. So our omega that we just found in rads per second is going to be 105 rads per second time is going to give us 2 seconds, and we're looking for theta because it asks for angular speed, express the angular speed in rads per second. So our basic equation again is omega equals theta over t. Now we're looking for omega, so we got to solve for omega, multiply t by both sides, and you get theta equals omega t. So we're going to use that formula. So we substitute everything we have here. Omega is 105 rads per second times t, which is 2 seconds, and that's going to give us 210 rads for theta. Okay, so that was the A part. Now the B part says, I'll just go to this page, the B part says find the angular displacement in 2 seconds. Okay. You know what? I just worked I'm sorry, this is the B part. The A part was converting it to this. This was A. This was B. Okay? And this is C. When I was reading it 2 seconds, we just did that. Find the linear speed of a point on the rim of the wheel. Okay? So we got omega, 105 rads per second. We have our radius is 1 meter, and it shows that on the wheel. I don't know why that does that. 1 meter. And we're looking for velocity this time. So the formula we used a while ago was velocity equals omega times r. And that's going to equal 105 rads per second times 1 meter. We get that, we get 105 meters per second. Now, why is it meters per second? Because the rad is a dimensionless unit. So this rad right here, it's dimensionless. So it's not meters or inches or feet or seconds or anything. It's just dimensionless. So when you do that, you end up with meters per second. Okay? And that's how you work those. All right. Now I want you to look on page 236. And in the middle of the page, you're going to see all these different formulas for linear motion and rotational. I'm not going to write all these down because you can look at them and just be wasting time on this lecture. But if you look at that, you'll see all the different formulas. And again, I'll give you this for anything you need for your test. But you'll see theta is angular displacement, omega final, omega initial, omega average, alpha, theta, times. You'll see all that, okay? So make sure that you look through that and know which kind of equations to use. So let's look at one more problem. And you're going to use these equations that I'm talking about. A rotating pulley 24 centimeters in diameter is rotating at an initial angular speed of 30.5 rads per second. The speed is steadily increased to 41.5 rads per second within 6.3 seconds. A, find the pulley's angular acceleration, and B, find the final linear speed of point on its rim. So let's write all this down. That's a lot of information. So first it says a rotating pulley at 24 centimeters in diameter is rotating at an initial angular speed. All right, so omega I initial is 30.5 radians per second. The speed is steadily increased to 41.5 rads per second. So omega final equals 41.5 rads per second. Okay, and then it says within 30 seconds. So time equals 6.30 seconds. And then it wants to know A, find its angular acceleration. So we're looking for A. All right. So if we look at the basic equations, we know we need one that's got final and initial and angular and time. So that one is going to look like this. WF equals omega initial plus alpha time. Alright. Now we need to solve for A, so we'll have to work this out where you move the equation on both sides, but it also gives you this equation. So A equals omega final minus omega initial divided by T. But you could actually solve it using that equation. So let's plug it in. So that's going to be 41.5 rads per second minus 30.5 rads per second divided by 6.30 seconds. You work all that out, you get 1.75 rads per second squared. Okay, and that's going to be alpha. So that's A. Now B says find the final linear speed of the point on its rim. So you're going to use the linear motion equations, okay? So our data, omega equals 41.5 rads per second. R equals 12.0 centimeters. And we're looking for our velocity. So it's asking for the final linear speed of a point on its rim. So the basic equation is V equals omega R. V equals 41.5 rads per second times 12.0 centimeters equals 498 centimeters per second for our velocity on one point of the rim. Okay? Now, for these problems on 9.1, page 237 and 238, I want you to work number 1, 5, hold on, 1, 5, 9, 17, 21, and 27. Okay? So that's not exact all of them that I had told you on the syllabus, so make sure you just do these. Now you're welcome to do more if it helps you study, but these are the only ones that I'll be grading, okay? So that's 9.1. And again, these are going to be due next week, okay? Your final will be, these will be due next Thursday, and your final will be the following Tuesday. Okay, so I'll be posting your video for this weekend too, and I'll probably go ahead and post the final early for you guys that are doing this homework early. All right, we're going to skip 9.2. Skip 9.2. Okay, skip that. We're going to go to 9.3. which is centripetal force. Okay, so Newton's law of motion apply to motion along a curved path as well as in a straight line. The centripetal force acting on a body in a circular motion causes it to move in a circular motion. I mean, that makes sense, right? So if you're in a car and you're going around a curve, your body moves too, doesn't it? So if you're going around the curve, you're going to move that way, okay? The formula for this is going to be F force, centripetal force, equals M, which is the mass of the body, V squared, which is the velocity, divided by R, which is the radius or the curve of the body. Okay? So let's look at a problem. An automobile of mass of 1640 kilograms rounds a curve of radius 25 meters with a velocity of 15 meters per second, or 54 kilometers per hour. What centripetal force is exerted on the automobile while rounding the curve? So let's write down what we have. Our mass of the body is 1640 kilograms. Our velocity is 15 meters per second. The radius of it is 25 meters. What is our force? Again, we're using this formula here. mv squared divided by r. So let's plug it in. M is 1640 kilograms times 15 meters per second squared. Now, you're going to have to square every bit of this, okay? Divided by 25 meters. So when you square 15 squared, it's going to be meters squared, second squared, okay? So this is going to end up being 14,800 kilograms meters per second squared. And remember, recall that 1 Newton is 1 kilogram meters per second squared. So this is also 14,800 newtons. Okay? And really that's it for this section. So it's pretty easy, okay? So for problems 9.3 on page 244, I want you to work number 1, 5, 11, and 15. Okay? 1, 5, 11, and 15. We're also going to, well, let's see. No, we don't need to skip. We need to do this one, okay? So 9.4 is power in rotational systems. Okay? So earlier we learned that power equals force times displacement divided by time. This will also equal work over time. Alright. So also, peak equals torque times angular displacement over time. And this also equals torque times angular velocity, because displacement divided by time is velocity, which will be tau. It's kind of a funny looking T. I know mine don't look exactly right, but you can look at it on page 245. Tau omega. Okay? Alright, so let's look at a problem. Okay, how many watts of power are developed by a mechanic tightening bolts using 50 newton meters of torque at a rate of 2.5 radians per second? How many in kilowatts? So let's write down our data. Tau equals 50 newton meters. Omega equals 2.50. Let me read that. Radians per second. And our power is what? So using our formula, power equals tau W, that's going to equal 50 newton meters times 2.50 rads per second. Now you'll notice that they just ignore the rads in the book. I like to put it on there because it's confusing with nothing there. But remember, rads are dimensionless, okay? So when you multiply this, you're going to end up with 125 Newton meters seconds, okay? And if you'll recall, 1 watt equals 1 Newton meter second. So that's going to equal 125 watts. And we know, if you just keep in mind of what different units are, we know power is in watts. So it makes more sense to have it in watts. Okay? So read through those, and you should be able to work those. Let me see if there's anything else. Let's see. Oh, don't forget that foot-pounds, 1 horsepower equals 550 foot-pounds per second. You might need that. We used it earlier too, okay? So for 9.4 homework, just a couple of problems. So 9.4, pages 248 and 249. I want you to work 1, 5, 11, 17, and 21. 1, 5, 11, 17, and 21. Alright, we're going to skip 9.5, I think. Yeah, there's no problems for 9.5, it don't look like. So for 9.6, I'm confused here. Hold on just a minute. Oh, I'm sorry, no. Yeah, we're just going to go to 9.6. Okay? 9.6, gears. If you want to read 9.5, it's talking about the transferring rotational motion. You might want to read that chapter too, okay? But gears are used to transfer rotational motion from one gear to another. The gear that causes the motion is called the driver gear. The gear that causes the motion is called the driver gear. And you know some of these may be on the test. Okay? I'm not sure where those big lines come from. If y'all know, please tell me. And the gear which the motion is transferred is called the driven gear. Okay? So there's many different shapes and sizes too. The formula for that is going to be T times N equals little t times N. T is the number of teeth on the driver gear. N is the number of revolutions on the driver gear, big N. Little t is the number of teeth on the driven gear, and little n is number of revolutions on the driven gear. So just remember, the driver is the bigger letters and driven is the smaller letters. A driver gear has 30 teeth. How many revolutions does the driven gear with 20 teeth make while the driver makes one revolution? So the driver gear, so that's going to be big T, equals 30 teeth. How many revolutions does the driven gear with 20 teeth make? So the driven gear will be little t, is 20 teeth. Alright, now it says in one revolution, so big N is 1 rev, and we're looking for little n. Our basic equation is Tn, capital Tn, equals little t times little n. Now we need to solve for little n, don't we? So when we solve for that, we end up with, you're going to divide little t to both sides. So I'll just do it real quick. So n is going to equal T, big N, over little t. And we have all that information, so we can plug it in. 30 teeth times 1 rev divided by 20 teeth. So that's, teeth are going to cancel. So that's going to give us 1.5 revs for the little n. So for every 1 revolution, the driver goes 1.5 revolutions for the driven. Okay? So you can work through those, and let's see if there's another one I'm going to do. Let's do one more. Let's do this one. So what if you had multiple gears? So find the RPM of gear D in the train shown in 9.18. So that's on page, oh, that's right beside it on page 254. So it shows you 60 teeth at 1600 RPMs, 30 teeth, 15 teeth, and 48 teeth. So let's write all that down. Gears A, B, and C are drivers, and gears B and D are driven. So N is going to be 1600 RPMs. Now, we got to look at the teeth. So it says A and C are drivers, A and C. So that's going to be T1, it's a driver, so it's capital T, 60T. And T2, which is C, is going to be 15T. And then B and D are driven, so little t1, which is B, is going to be 30T. And little t2, which is D, is going to be 48T. And N, we're looking for how many, the RPMs, okay? So now, if you want to see this, it's figure 9.18 on page 254, because I cannot draw that. So our basic equation for multiple ones are going to be N times T1 times T2 equals N, little n, times T1 times T2, little t, okay? Now we need to solve for N, so we got to solve for here. So we're going to divide both sides by T1, T2, so those will cancel. So now we have N equals capital N times T1 times T2, big T1, T2, divided by little t1, little t2. So we plug it in. N is, capital N, is 1600 RPMs times big T, 60 teeth, times big T2, 15 teeth. All that divided by little t1, 30 teeth, times little t2, 48 teeth. Okay, so this teeth cancels, this teeth cancels, this teeth cancels, and this teeth cancels. So all the teeth cancels, so we end up with RPMs, and that's going to be 10,000. I'm sorry, too many zeros. 1,000 RPMs, not 10,000. 1,000 RPMs for N. So big N was 1,600 RPMs. By the time we work this out, little n is going to be 1,000 RPMs. Okay? So for these problems, this is 9.6, pages 256 and 257. I want you to work number 1, 5, 7, 11, and 23. Okay? 7, 11, 1, 5, 7, 11, 23, and I forgot this one, 17. Okay? Alright, so that's the end of chapter 9, and this will be the last lecture video that you'll have. Again, the final's going to be, I'll post it early, but it's going to be due by midnight on Tuesday, August the 8th. Tuesday, August the 8th. All homework and test will be due that day. I'll have to have the next day to calculate all the grades, okay? So if you have any questions, let me know, and be looking for the lecture video or the video for the review for the final. Probably post it sometime this weekend. Thank you. You guys have a good night.